This is our sixth part of logarithms. Again, we're going through samples of how to solve logarithms, hoping that you can pick this up. Here again, the definition of logarithm is log base b of a, where b has to be greater than 0 or positive, but it cannot be equal to 1. And then also a has to be positive also. So now we go to our last set of problems to solve. Again, this is a u substitution where we let u equal e to the x. You'll notice an e to the x in each of these terms. With u substitution, you rewrite this to show that the powers are power on a power. These two bases are now e to the x, and when you substitute in u, you find out you can factor these. These are a perfect factor. Each of these represents, by setting them equal to 0, one of the solutions possible. Since the original problem wasn't u, it was e to the x, we substitute that back in. And to solve for x, we need to write these both as natural logs. So base e here, this is something we look up on the calculator, and we get these two different answers. And again, the inaccuracy, the closeness that a calculator will give you still is really great. And so we want to check these. We plug them in. And with a calculator, this is not a great deal of work. But with the use of parentheses, we find out that the first one checks, and then we plug in the second one. And again, using parentheses properly, we find out that that one checks also. Remember, you can't always assume that these will check. Okay, the next one is a illustration of this log rule that I'm highlighting right here on the right. The b to the log base b of a is a. You'll notice that's exactly what this one is. Base 7 of log base 7 of 23 is 23. So another illustration of that would be 5 log base 5 of 3x minus 2 simplifies into 3x minus 2. Again, there is the e rule that would just go right along with this one right here. E to the natural log base e of x is x. So these are usable in situations where we may want to emphasize that rule. And here we have one that does not have a matching base, yet it has the x by itself. So once again, this is something you would have to put into the calculator, and you would have to use the parentheses up here to group this together. Not only that, you would have to use base change, because this is log of 19 over log of 7. All of this would have to be with your exponent button, putting that into the numerator. This is definitely one that you want to check on your calculator. Be familiar with how your calculator works. Don't go into a test or an exam and borrow somebody's calculator. You need to know your own. You will have problems if you don't do that. The next one is, again, we're just finishing out doing problems that are slightly different than what we've done before. You'll notice this one does not have a matching base 3 to a matching base 3. Instead, it's to a base 2. Notice these two. That reminds me of this log rule down here. The n exponent comes out to the front. You can't see it right now. It's been blocked out. That means that this exponent, x, comes out to the front, and I just simply divide by the log to the other side, log base 3 of 2. Of course, this is going to cancel and leave me an x here. I'm going to have to do this on the calculator, but I also have to keep in mind that that is a Base change, here's the formula here, base change. I'm going to have to apply that here. Try that out on your calculator. Make sure you do it correctly. Use a big parentheses in this denominator to keep all of that base change together. If you don't, you're not going to get this number. Check your calculator. The next one looks a little more complicated because of its denominator. And of course, we can't leave a denominator with the x we're trying to solve for. We can't leave that right there. So we're going to have to take that 1 plus e to the negative x power times both sides, and it, of course, will cancel right here with this one. That's gone. That'll be a 1. The 30 is going to divide over to the 525, and when we divide that out, we get 17.5. And of course, we have to bring the 1 over. We're trying to get the x by itself. So now we see this e to the x, and we think, well, let's write this as a logarithm, base e. And notice I put the negative x over here. I didn't lose that negative x. That's a little sign problem that you would have in your solution. And then I look up the natural log of 16.5, and this negative sign divides over and makes that a negative. There's my approximation sign again. Okay, getting near to the end here, we have a log base 3 all the way through. That reminds me of the equality rule right here. And it also reminds me of the product rule, which has sums of logs in it. So I want to push these two logs together, condense them into a single logarithm. And because I have a single log base 3 equal to a single log base 3, I can eliminate the entire log base 3, set the antilogs equal to each other, multiply, distribute through, combine like terms. Greatest common factor, don't forget the greatest common factor. That means that x equals 0 and x squared equals 16. The square root of 16, there's 2, plus or minus. Now you'll notice over here I've already checked the 4. I've plugged the 4 into the original equation. You don't want to plug it into anything besides the original equation. And when checking it, it comes out as 32, log 32 equals log 32. That 8 times 4 should be down here. So that tells me that checks. I have two other possible solutions. The one is 0. Again, I plug it into the original problem. Now there's a problem here. You can't have a 0 right there. Can't have a 0. That is no solution. So a no solution and a negative number here, no way. Phi, the answer will not check. That brings me to negative 4, so I plug it into the very same original logarithm. And again, you can't have the natural log base, the log base 3 of negative 4. None of these, this would not work. So the only one that works is 4. That tells me 4 is the x-intercept. Nothing bad to talk about with the 0 and the negative 4, except they're just not on the graph. They will not check. They are not x-intercepts. Okay, last two. We have here a earthquake illustration using magnitude. Here are some earthquakes in the past. We're Californians. We noticed here the Northridge quake is 6.3. We've had even recent quakes in the 8s in the world. So the intensity of these is related to the magnitude on the Richter scale. Richter, that's the R, log base 10 of I, which is intensity, over I sub 0, which is the initial intensity. That's when there is no earthquake. It's a 1. It can't be 0. You can't have a 0 under here. So really, that's kind of eliminated. So we're going to take the 6.3 right here, equal to log, notice base 10, of I, capital I, and reverse it into an exponential, and we find out that's almost 2 million. That's the intensity. And then we try the 8.3 on the Richter scale, and we find that that one is 100 times more powerful. It has 2 more tens in the product of it. That moves my decimal. So if I divide, this kind of goes crisscross. If I divide the 8.5 by the 110 to the 6.5, I find out it's 10 to the second, which is 100. And now we move on to our last logarithm problem, and that is the doubling of money. I would like to take my $10,000 and I'd like to put it at a 6.275% interest rate compounded continuously, and I want to double my money. Well, the formula for that is PERT. That's principal times e to the exponent rate times time. This is a popular formula, so I would plug that in. The 10,000 is my original, my P, my original principal, and I want to double my money, so I want it 20,000. My rate as a decimal is 0.0675 times time. How much time does it take me to double my money? So I divide 10,000 into 20,000 and get 2. Makes no difference whether I used 1,000,000 here and 2,000,000 here. I'm still going to get 2. How long does it take me to double my money? Well, I write this as a natural log. There's my e, and e of 2 equals the rate times time. Divide by the rate. Again, just being careful on the calculator. It takes me 10.27 years to double my money in an investment, maybe the mutual fund, probably not in a bank, but in a mutual fund. And this is a good example of how over time money invested can double, triple, quadruple. We could change this anyway to show the advantages of savings, and we know it's wise. We should be wise and save money out of every paycheck. Well, that's my sermon. Hope this has helped you on logarithms to be a little clearer. I have some things on exponentials that go with the first part of this. You can look for those also on either YouTube or on my haiku. Thank you. Hope this was helpful to you.